Yeah. So last time we were doing rolling motion. Okay, we had completed your half of rolling motion was done. Okay, I told you one of the cases of rolling motion was remaining. Okay, so we are going to complete that today. So your chapter will be over today. Huh? Acha. So last time you had calculated rolling motion on an inclined plane. Okay, we had calculated rolling motion on an inclined plane. We calculated the values, okay, different values which can be asked in questions. Okay, first one was velocity. Okay, what should be the velocity of an object? Okay, which is showing pure rolling on the inclined surface. Second was acceleration. Achha, before we move further, okay, let's try to simplify the formulas, okay, so that you are able to remember it a bit easily. Okay, so for that you need to learn a new term. Okay, so that is not a very common term. Okay, even if you means let it go, okay, it is not an issue. Okay, it is not very regularly used, but you should at least know about the term, that there is some term like this. It is called as radius of gyration. Okay, gyration pronunciation.
Sir, your
Okay,
voice
but
is cracking.
my voice is cracking.
Yes, sir.
Everybody, acha. So just let me. Okay, okay, okay. Everybody is facing this. Okay, so just let me leave and join again. Okay, so now is it clear? Now am I audible?
Yes, sir.
ठीक है. Ah, now I guess it is clear, है ना? अच्छा. So
Yes, sir.
uh, ठीक. Now there is a term, okay, called as radius of gyration, whatever, whichever you want to pronounce it. Okay, you can pronounce it that. Okay, it is represented by k. Now what is the meaning of this radius? Okay, it is very much similar to your center of mass in linear motion. Okay, it is very much similar to your center of mass in your linear motion. Like suppose I have a disk. Okay, suppose this is a disk, and from the center of mass we are passing an axis. So the the moment
Yes.
of inertia. Yes.
Sir, are you presenting the
There's
screen?
a
So,
screen. Yeah.
Yes, I am presenting the screen.
sir, we can see the team's screen.
So we
Okay.
can see the teams. Not yes.
So your screen is not visible, sir.
Okay. Just let me again join. Must be some network issue. I don't know what is happening today. ठीक है. Now is the screen visible to everybody?
Yes, sir. Now it's visible.
ठीक है. अच्छा जी, ठीक है. I was planning to get Geo fiber, but Geo has not yet reached me. Okay, so when it reaches me, I will definitely take the connection. No problem in that. But I tried. Okay, I have already tried Geo fiber and Airtel Extreme. Both I have tried, but okay, they are not available now in my area, so can't help. Okay, so we will just have to manage with this only. Okay, that is wireless networks. Okay. So let's come back to radius of gyration. Okay, so here just see what I wanted to say is that what is radius of gyration is. So see, it is something similar to center of mass. Okay, what do we do in center of mass? बस. ठीक है, शांति है ना, cool down. ठीक है, chill. अच्छा. Now, what is radius of gyration is? See, it is very much similar to center of mass. How in linear motion, in translatory motion, whenever we have to study its translatory motion, okay, whenever we have to study the path of the translatory motion, okay, what we do is we remove the object. Okay, we just keep the object aside and study its center of mass. Okay, this is the concept of center of mass. No problem. But if it is rotational motion, okay, what we do is we assume it that whatever is the effect of rotation of this disk, okay, it will be very much similar to a point object at a distance k of the same mass. Okay, if you rotate this point mass at a distance k, and if you rotate this disk, their moments of inertia will be same. Like in case of disk, the moment of inertia comes out to be mr square by 2. Okay, it comes out to be mr square by 2 for a disk. Okay, about an axis passing through the center of mass. You know this. Okay, we have already done the list. Okay, and what is the moment of inertia of this point mass? Okay, for point mass, I already told you there is only one formula, that is mr square. That's it. So mass is how much? M. R is how much? K. mk square. Okay. So if you want to replace this disk with a point mass and observe the rotational motion, okay, or to simplify the rotational motion, okay, what we do is we just equate ICM with I. Okay, we just equate the moment of inertia of the two situations. Okay, so if you equate it, it will be mr square by 2 is equals to mk square. So from here, you get the value of k as r by root 2. So I can say that radius of gyration of disk, okay, about axis passing through center of mass is how much? It is r by root 2. That means I can replace my disk with a point mass which is at a distance of r by root 2, from the axis. Okay, this is the concept, this is the meaning of radius of gyration. Okay, so in a similar manner, you can represent any shape. Okay, this was one example. Okay, you could have represented ring also. This was disk. Okay, let's write here disk. Okay, you could have represented it with a ring also. Like, let's see again, ring. Suppose I have a ring, and it is rotating about its axis like this. Okay, it is rotating about its axis like this. So ICM, how much will be ICM? mr square. We know this. It will be mr square. Now what I can do is I can convert it into a point mass. Okay, I can convert it into a point mass which is at a distance k from the axis, which is at a distance k from the axis, and it is giving me the same rotational effect. It is giving me the same rotational effect as ring. So moment of inertia should be equal. So mr square is equals to mk square. Gets cancelled. So from here you get the value of k as r. So for a ring, you can see that k is r. Okay, so it is somewhat like center of mass. It is somewhat like center of mass. Okay, in center of mass also the same thing you do. Okay, that you replace the complete object with a point mass at the center of mass. So here, since we are studying rotational motion, okay, there should be some rotation involved, na? Okay, so what we do is we replace the disk with a point mass. Okay, so what do we get? What is the final conclusion? That any moment of inertia can be represented as mk square in general. Okay, any moment of inertia, the moment of inertia of any object can be represented as I is equal to mk square. Okay, so this becomes a general formula for moment of inertia. Okay, suppose you want to write the moment of inertia of disk, you will say mk square. Simple. K is r by root 2. Okay. If you want to write the moment of inertia of a ring, you will say it is mk square, where k is r. Khatam. Okay. Suppose you want to write the moment of inertia of a hollow sphere, you will say it is mk square, where k is under root of 2 by 3r. Khatam. Okay. Now, how did I get that value of k for hollow sphere? Simple. You know the moment of inertia about its center of mass, equate it with mk square and solve the value of k. Okay, so it is just a new representation. It is just a general representation of moment of inertia. Okay, is it understood? It is clear. Or anybody has any doubts? Okay, so we will use this radius of gyration or gyration, whatever, to simplify our results. Okay, once I simplify the results, na, you will be very easily able to remember the formula. Okay, so I will just first write this. I will show you how the formula becomes simplified. Okay, I guess everybody has written this. Acha. Now let's come back to our pure rolling on inclined surface. Okay, just see the formula for VCM. Okay, if you see the formula for VCM, I had written something like this: 2mgh upon m plus I by r square. Something like this I had written. Huh? This was the formula for VCM. Okay, now it looks a very complicated kind of formula. Like it is something like कि क्या है ये, है ना? But now see, I have established that for any object in general, okay, the moment of inertia can be written as mk square. Okay, for any object, moment of inertia in general can be written as mk square. So do what? Just replace this over here. Okay. As and when you replace this, see what happens. It becomes under root of 2 mgh upon m plus mk square by r square. Okay, you can see from the denominator that m is coming out as common, and there is a m in the numerator also. So this m cancels out. Okay, this m cancels out. So this becomes under root of 2gh upon 1 plus k square by r square. Now see, very simple. Suppose pure rolling was not there. Okay, suppose that no kind of rolling was there. The object was simply just straight falling down. Okay, object was simply just straight falling down the inclined surface. Then the final velocity at the bottom, you know that it will become under root of 2gh. Okay, you have calculated this in conservation of energy and all. You must have done this. Okay, so under root 2gh is the final velocity. Now, since there is a rotational effect, since there is a rotational motion involved with it, there is an extra factor of 1 plus k square by r square, 1 plus k square by r square being introduced in the formula. Okay, this is also called as rotational factor. This box one is called as rotational factor. Okay, because of rotational motion in the object during the inclined plane. Okay, the extra term which is being introduced is this 1 plus k square by r square. If suppose there won't have been any rotational motion, so k will be 0 because moment of inertia is 0. Okay, if k is 0, the term automatically vanishes. Okay, in the denominator there is only 1, so the final velocity becomes under root of 2gh, which is consistent with conservation of energy. Okay, when there was no rolling motion, there was no rotational motion. Okay, so this extra term is called as the rotational factor. Okay, so in this way you can easily remember that what will be the final velocity. Okay, what will be the velocity when it reaches the bottom? Simple, write the general formula under root 2gh, but divide it with a factor. What was that factor? That factor was 1 by k square plus r square. That's it. This is the final VCM. Okay, this is the final VCM we had calculated. Okay. Similarly, okay, for acceleration also. Regis, what is Regis? It must be rigid. Rigid body means that the object is solid. Okay, rigid body means that it is having a fixed axis of rotation and it is solid. Okay, there is a possibility like suppose you fill a jar with glass of water, with water, suppose, and you are rotating that jar, you are rotating that cylindrical object. So what will happen? That water will come out. Okay, water will move out from that. So in that situation, the body is not rigid. Okay, it is changing its shape. Okay, water is coming out means mass is changing, so it is not a rigid object. But if it is a solid cylinder, suppose it is a jar filled with metal. Okay, it is filled with aluminium or something. Okay, then if you rotate that, no mass will change. Okay, the mass will not come out. Okay, so that is a rigid body. So in our syllabus we only have to study about rigid only. Okay. Yes.
Okay, understood, sir.
Acha. So this is the first thing, okay, which we calculated in inclined plane, pure rolling on the inclined plane. That is this velocity. Okay. Second was acceleration. Okay, if you remember, we had calculated the formula also. Okay, it came out to be mg sin theta. You can just see your notes. You must have written in your notes plus I by r square. Okay, this again mg sin theta upon m plus I by r square. Again, you see this is not a very good formula to remember. It is a weird kind of relation. Okay. So again, what we can do is we can replace it as mk square. I is equals to mk square. So if you replace I as mk square over here, again you will see in the denominator that m is coming out to be common. M is coming out to be common. So m cancels out. You will be left with g sine theta upon 1 plus k square by r square. Okay, 1 plus k square by r square. Again, if you see, this is the final formula. Okay, ACM is equals to g sine theta upon 1 plus k square by r square. Again, if you see that g sine theta would have been the acceleration if there wouldn't have been any rolling. If rolling was absent, then if friction was not there, if rolling was not occurring, then g sine theta would have been the acceleration, okay, along the inclined plane, obviously. Okay, but since rolling is also there, rotational is also there, okay, again you can see that the same rotational factor 1 plus k square by r square is being divided over here. Same rotational factor is being divided over here. Okay, so this thing, just simplifies your formula. Okay, so now you can remember, that uh, uh, the what will be the acceleration, what will be the velocity, okay, in pure rolling. Okay, it is everything similar to your normal motion, just a rotational factor is being introduced over here. That is 1 plus k square by r square is being divided every time. Okay, so in this manner you can remember the formulas. Okay. Acha, note one thing that if you had seen the previous formula of VCM, okay, you could have said, you would be saying that ki, sir, velocity is dependent on mass. Okay, the final velocity of the object is dependent on mass. But when you see the simplified formula, okay, you can see that it is independent of mass. Okay, mass is not there anywhere. So which is true? Which is true? Okay, the second statement is true, that the velocity and acceleration also, if you see, okay, so you can just take a note over here that the VCM and ACM are independent of mass of object. Okay, so again it is same as linear motion. Okay, in translatory motion, if in without rolling motion, if you would have seen the velocities and acceleration, they were independent of mass. Okay, whatever be the mass, I don't require the mass. Okay, it is not necessary to me, it is not important for me. Okay, so here also the same thing. Okay, mass, what is the mass? I am not interested in that, but how the mass is, present. Okay, whether it is in the form of a sphere, or it is in the form of a disk, or is it in the form of a cylinder, that is important to me. That is why K is there. K is representing that thing. Okay, if you change the object from sphere to disk, your K will change, A center of mass will change. Okay, so shape, it is dependent on the shape, but not on the mass. Not on the mass. Okay, mass can be 10 kg, 25 kg, 100 kg, doesn't matter. The acceleration will be this much only. Okay, so it is independent of mass. This is, a theoretical question can be made over here. Okay, which of the following is correct? So one statement will be that in rolling motion, in pure rolling on the inclined plane, okay, velocity is independent of mass. Final velocity is independent of mass. So it is a true statement. It is a correct statement. Okay. So these are the things you have to remember. Okay, take care about. Okay, so write this. Okay, I guess everybody has written this. Now let's see a question. Okay, regarding inclined surface. Okay. Okay, so this is the question. Okay, that there is a solid sphere which is rolling without slipping. Understand this. Understand this. Rolling without slipping also means pure rolling. Okay, this is another term used for pure rolling that is called as rolling without slipping. Okay, so this is also called as pure rolling. Okay, because I already told you that the friction there was static. Okay, friction at the point of contact is static. So static means what? There is no slipping. Okay, if kinetic friction would have been there, then there would have been slipping, like in drifts. Okay, so here it is not the case. Okay, it is rolling without slipping. That means pure rolling. Achha. Now, if it is pure rolling on a level surface with a speed of 2 meters per second, that means what is this speed representing? This speed is representing the velocity of center of mass. Okay, these terms they have not mentioned in the question. Okay, they will not be mentioned in the question. You have to understand it that if it is pure rolling with 2 meters per second, that means it is linear velocity. Okay, and linear velocity in rolling motion is VCM most of the time. Okay, it is only VCM you can say. Okay, VCM is the only thing which has linear velocity in that. Okay, so this is VCM. Acha, now what the question is saying that I have a horizontal surface and this is an inclined surface. This is at an angle of 30 degree from the horizontal. Okay, now there is a solid sphere. Okay, with a velocity of center of mass as 2 meters per second. It is pure rolling. That means it must be having some omega also. It must be having some omega also, but I am not interested in that. Okay, I have not been given any values of that, nor I have been given the radius for that. Okay, so what should be done is that first of all, what will happen? You can understand that as it goes up the inclined surface, its velocity will keep on decreasing. Its velocity will keep on decreasing. Okay. At one point, its final velocity will become zero. At one point. Mute your mic. Okay. At one point, the velocity will become zero. Yes. Any doubts? Mute your mic. Mute your mics. Please mute your mic. Mute your mics. Yes, everybody just mute your mics. Whoever mic. I have to join for that. ठीक है ना? So where were we? हाँ, that we had a solid sphere rolling up an inclined surface. So it is understandable that it will go up till some height. ठीक है? Now understand this, while it is going up the inclined surface, at that time also, at that instant also, it is showing rolling motion. ठीक है? At that time also it is doing rolling motion. ठीक है? So if it is still doing rolling motion, what I can say is that by the time it reaches height h, ठीक है, its kinetic energy, that is translatory as well as rotational, both will be zero. In fact, I can say that omega will also become zero by the time it reaches point B. Suppose it was not pure rolling. Suppose, just imagine that if it was not pure rolling, then omega cannot become zero. Okay, if it was not pure rolling, that means friction was not there. Okay, if friction was not there, that means there was nothing to stop the rolling motion. Okay, its linear translatory motion will be stopped by the height. Okay, that translatory kinetic energy will be converted into gravitational potential energy. But what about the rotational kinetic energy? Okay, that rotational kinetic energy will still be there with the the sphere. Okay, so that kind of question might be asked. That is why I'm telling you it. Hai. But if it is not asked, if this is the situation, okay, in most of the cases, this is the situation that what is the height it will go up to and stop. Okay, stop means neither translatory velocity nor rotational velocity. Okay, both the velocities have become zero. So what I can do here is, again, okay, I told you on an inclined plane, whenever velocities and all is given, okay, we apply conservation of energy. Okay, so for A to B motion, I will apply conservation of energy. So I can write kinetic at A plus potential at A is equal to kinetic at B plus potential at B. Let's now calculate the kinetic energies and potential energies at these 2 points. So first of all, potential energy at A. Okay, if you see potential energy at A, this is your ground level. Okay, this is your ground level. So this is your reference. So here potential energy is zero. So potential energy on the ground level is zero. Okay, you might be thinking, sir, why not mgr? So I told you that this height h will be very much smaller, very much large compared to the radius of the sphere. So we can neglect the radius of the sphere. I told you this in derivation also. Okay, so it is very much larger, so you can just neglect it, that there is no mgr. Acha. Now this is potential energy. What about the kinetic energy? At A? Okay, kinetic energy at A can be written by the summation of two terms, that is translatory plus rotational. Okay, because at A point it is showing rolling motion, so it will be kinetic of translatory plus kinetic of rotational. Okay, we will see that how to write that. Let's talk about point B. Okay, kinetic energy at point B, you can see that it is zero, it is at rest, it is completely stopped. And what about the potential energy at B? Okay, it is at a height h. Let's assume its mass is m, so it is mgh. Okay, this will be mgh. Acha, so let's put these values over here. Kinetic energy at A can be written as translatory plus rotational. Translatory kinetic energy is what? Half mv square. Half mv square. Rotational kinetic energy is what? Half I omega square. Half I omega square. Okay, this is the total kinetic energy plus potential energy at A. Potential energy at A is 0. Kinetic energy at B is 0. What is potential energy at B? mgh. This is the h which I want to find out. This is the h which I want to find out. Acha. Now see, velocity is given to me as 2. Okay, no problem in that. Moment of inertia, I. Okay, so here we have to calculate the moment of inertia of a solid sphere. It is given in the question that the object is solid sphere. So moment of inertia of solid sphere is what? ICM, we have calculated it as 2 by 5 m r square. Okay, we have already written that. Okay, that ICM is 2 by 5 m r square. So I can be replaced as 2 by 5 m r square. Okay, into omega. Now omega is not given to me. Omega is not given to me, but it is given that pure rolling is happening. If it is given, I can write what? I can write the condition for pure rolling. What is the condition for pure rolling? VCM is equals to omega r. VCM is equals to omega r. I can write this. So omega can be written as VCM by r. Omega can be replaced as VCM by r whole square. Okay, this is equals to mgh. Now from here you can see that r square will cancel out. M is coming out to be common on both the sides, so m will also cancel out. So whatever you solve, okay, this will be 4 by 2, that is 2 only. 2 plus 1 by 5 VCM square. VCM is also 2, so let's just replace it as 2 square. This is equals to g into h. So whatever the h comes out, it will be in only, no problem. Whatever it comes out will be your final result. Okay, h can be calculated from here. Okay, so this is how you can calculate your height. The height it will travel. Okay, hope it is clear. Any doubt in this? Okay, it is a simple question of conservation of energy just because of pure rolling. Yes, yes.
Sir, how did you get 2 upon 5 mr square?
That is the moment of inertia of your solids. I had given you the list and moment of inertia, na? The standard moments of inertia of different shapes. Okay, so if you see the solid sphere, moment of inertia of solid sphere, na, it was written as 2 by 5 mr square.
Okay, sir.
है ना? ठीक है. Any other doubts, anybody? ठीक है. So this is how you calculate moment of inertia. Height. ठीक है. This is how you apply conservation of energy in rotational motion. ठीक है. Everything is same. ठीक है. Everything is same. Just this is a new term that has to be added. That's it. Everything else is same. Everything else is same. Okay, only a rotational kinetic energy is also introduced in the system. That's it. Okay, so these kinds of questions will be asked. Okay, these kinds of questions will be asked to you in exam. So just be prepared for this. Okay, so I have done a question on that also. Achha, time taken to reach the bottom. Okay, already discussed in the last class that the object with more moment of inertia, okay, the object with higher moment of inertia will have a lower acceleration of center of mass. Lower acceleration of center of mass means it will take more time to reach the bottom. Okay, so I guess you can compare the moments of inertia. You have the list, you have the values, you have to remember those values. Okay, then only you will be able to compare the time taken to reach the bottom. ठीक है, हाँ मतलब whatever it comes out, ठीक है, I have not calculated it, ठीक है, it is 4, 10, 14 by 5, 14 by 50. How are you getting 28? H is coming out to be something in the fraction of 14 by 50. H is 14 by 50 meters.
Okay, sir.
So it's 0.28, right?
Yes.
0.28.
Where? Which? Value of H. And a value of H, na, हाँ, it is 0.28. Yes. Something 0.28. हाँ, ठीक है, 0.28, 14 by 50. ठीक है. How are you able to do wrong after this? I have calculated almost everything. ठीक है, so improve your calculations, है ना? अच्छा, if pure rolling, ठीक है, if you want that, let's see. ठीक है, just if you want to write it, ठीक है, write it. I will just show it in brief. ठीक है, I am not going to calculate everything. I will just show you in brief that what will happen if pure rolling was not there. ठीक है, suppose it is like this, that here it is showing pure rolling on the horizontal surface, it is pure rolling. ठीक है, but on the inclined surface became what? It became smooth. This became smooth. ठीक है, friction is not there. Now if this is the situation, just try to understand that it has a velocity and it has a omega over here. It has a velocity and it has a omega over here while on the horizontal surface. But as it goes up the inclined surface, it is going to lose its translatory kinetic energy. Okay, it is understandable that as an object goes up, its velocity decreases. So velocity will become zero. Its velocity will become zero, but final angular velocity will remain the same as initial angular velocity. That won't change. Okay, that won't change. If that is not changing and you want to find this height, what we will do is we will again apply conservation of energy, no doubt in that. Again, conservation of energy will be used, but now when you write kinetic energy at A plus potential energy at A, let me write this, kinetic energy at B plus potential energy at B. Now see, kinetic energy at A will be what? It will be half mv square plus half I omega square, no doubt in that. ठीक है, potential energy will be zero. LHS will remain the same, exact same. ठीक है, even VCM you can write this as omega r over here. ठीक है, so left hand side will remain exactly same as we have calculated. But on the right hand side, where I was writing net kinetic energy to be zero, this statement will become wrong. Because at point B, now it has zero translatory kinetic energy, but it has some rotational kinetic energy. So the kinetic energy on the right hand side will become translatory 0 plus rotational is how much? Half I omega square plus mgh. ठीक है, now since it is smooth, the omega initial and omega final are same. This is omega initial, this is omega final. So since both are same, it will cancel out. So simply what you will be left with is half mv square is equals to mgh. You can say that whatever is the translatory kinetic energy will be converted into gravitational potential energy. Okay, when friction is not there. In previous question, what was happening? Your translatory plus rotational kinetic energy was getting converted into gravitational potential energy. But here, when it becomes smooth, only the translatory kinetic energy will get converted into gravitational potential energy. Okay, so this is a variation if friction is not there. This is the variation which can be created if friction is not there. So keep this in mind. ठीक है, it is not a very common kind of question, but yes, ठीक है, there is a possibility, there is a high probability that it can come in your tests. ठीक है, this regular test which you are having on Sundays. ठीक है, part test and all. ठीक है, so keep this in mind. अच्छा, so this was everything about pure rolling on inclined surface. ठीक है, I guess I have told you that pure rolling on inclined surface, if you are unable to remember the formulas, at least remember conservation of energy. ठीक है, I have done 2 questions. ठीक है, not 2 questions, 1 question only, but it has 2 parts. So conservation of energy was the thing which I was using. ठीक है, I have not used formula anywhere. ठीक है, so formula is not as important as it looks. ठीक है, in physics I have told you many times that formula is not as important. ठीक है, so just try to remember the steps, procedure. ठीक है, the logic behind it, है ना, so it will be easy. अच्छा, ठीक है, so let's move on. ठीक है, the case, ठीक है, I told you there were 2 cases. One was pure rolling on inclined surface, the other was pure rolling on horizontal surface. So let's see. That is pure rolling on horizontal surface. Okay, second case is pure rolling on horizontal surface. Okay, now see, I am going to do again the derivations here. Some derivations will be there about acceleration and friction. Okay, but the result is again important. Okay, you have to keep in mind what is the result I am getting from that. Okay, because see, as such friction, rolling on horizontal surface is very less asked topic. Okay, it is not a very common topic, but it is like, means it is very easy. Okay, if you remember the concept, if you remember the results. Okay, so try to remember the results over here, to remember the formulas and all, but try to remember the result which I am going to tell you. So let's see. Okay, so I have a spherical object like this. Okay, its center of mass is somewhere over here. This is its center of mass. Its radius is r and mass is suppose capital M. And now see, I have told you that friction is required. Okay, friction is necessary. Okay, that is also not a exactly true statement. We will just nullify that statement over here only. Okay, but for now let us assume that there is friction. Now if it is showing pure rolling, okay, that means there must be some force acting on it. Okay, there must be some force, external force acting on it, because if you keep suppose you are having a cylinder on the ground, will it start? Okay, on a horizontal surface, if you are keeping a cylinder, okay, will it start to roll on itself? Okay, it cannot start pure rolling by itself. Okay, what it needs is a push or a pull, whatever. It needs an external force. So suppose I have applied an F external at a height h from the center of mass. Okay, let the center of mass be C. Better. Okay, so now if you are applying a force at a height h from the center of mass, now you can say that yes, there will be some kind of rolling motion in the object, in the surface on the object. Acha. Now just try to imagine if there is an external force acting on it. Okay, if there is an external force acting on it and it is showing pure rolling. Okay, pure rolling means what? That VCM is equals to omega r. VCM is equals to omega r. That won't be required over here much, but still VCM is equal to omega r is the criteria. Now see, if it is if external force is acting on it, there must be some kind of static friction at point A. Yes, there must be some kind of static friction at point A. Now, if you remember, static friction is a self-adjusting force. It is a self-adjusting force. That means you cannot predetermine its magnitude or direction. You cannot predetermine its magnitude or direction. Okay, but what can we do? We can assume. Okay, I cannot definitely say कि हाँ यार the friction will be in this direction only. Okay, I cannot say this, but I can assume कि let's see if the friction is in this direction, then what will happen. Okay, so I assume that the static friction which is acting on the point A at point A is in the forward direction. Just assume it. Okay, assuming. Okay, let's just write it here. Assuming that Fs is acting at point A in the given direction, in the direction which we have drawn. Okay, so if you are assuming it, if the answer comes out to be positive, then the direction which I had assumed was correct. Okay, and if it is coming out to be negative, the direction which I have assumed is wrong. Okay, we can say this much. है ना? Acha. Now see, it is showing pure roll. It is having translatory as well as rotational motion. It is having translatory as well as rotational motion. That means it must be having some acceleration of center of mass because of translatory motion, and it must be having some alpha associated with it because of rotational motion. Okay, and I guess this is clear. Acceleration of center of mass, it is showing translatory motion, and because of friction there was rotational motion in the inclined surface. Okay, so it was showing rotational motion also, so that is why when they combined it started showing rolling motion. So same case here. Okay, since it has some center of mass, acceleration of center of mass, it is showing translatory, and if there is friction there will be angular acceleration. Okay, acha. Now if I'm talking about translatory motion, what I can say is that F net is equals to MACM. I can write this equation for translatory. This is translatory motion. Okay. And rotational motion. What about rotational motion? I can write torque net is equal to I alpha. Okay. For rotational motion, I can write that net torque is equals to I alpha. Okay. Now let's take it one by one. Let's take translatory motion first. So let's see translatory motion first. The net external force, if you see, okay, acceleration of center of mass is considered as positive, so this direction will be positive. So you can see that the net force on the object is F external plus Fs. Okay, it is F external plus Fs. That's it. Okay, you can see that both are in the same direction, so they will be added up. So net force on the object becomes how much? It becomes F external plus Fs. Or I had told you another way. That write the center of mass only. Okay, forget any other point. Okay, just concentrate on center of mass and draw all the forces on that center of mass. So you can see here F external is like this, and even friction is like this at the center of mass. So what will happen? They will combine. Okay, these are just small tricks to understand the motion. Okay. Acha. So F net became F external plus Fs. This is equal to MACM. This is equal to MACM. This is your first equation. Okay. Now let's move on to second, that is rotational. Okay. So for that we need the net torque. This is net torque. Okay. Net torque about which point? About the center of mass. Okay. We are calculating everything about center of mass only till now. So net torque about center of mass. So let's calculate the torque. Now, while calculating the torque, you can see there are only two forces. Okay, there are only two forces. So there must be only two kinds of torque. That is one because of F external and one because of Fs. One because of Fs. Okay. Now, what is the torque due to F external? Simple. F external force is this. Perpendicular distance is h from the point, from the center of mass. So magnitude becomes F external into h. F external into h is the magnitude. What about the direction? The direction, again, remember I told you how to calculate the direction. Forget any other force. Just concentrate on this force. Okay, forget any other force. Suppose I am applying a force F like this. Okay, at a height h. If I am applying a force F like this, the body wants to rotate like this. Body wants to rotate in clockwise direction. Okay, so if it wants to rotate in clockwise direction, its torque will be clockwise. Okay, similarly for small fs. Okay, small fs, that is friction force. The force is how much? Force is Fs. And what is the perpendicular distance? Again, you can see it is r. Perpendicular distance is r from the center of mass. So Fs into r is the frictional force, torque due to frictional force. Sorry. Okay. What about the direction? Forget any other force. Forget any other force. Just concentrate on friction. Okay. If friction is being applied, and if you apply a force on this like this, so the tendency of the object to rotate is like this. Tendency of the object is to rotate in the anti-clockwise direction. So this will become anti-clockwise. Okay. Now see here. Which direction should be considered as positive and which as negative? It is similar to linear motion. Okay. How did you consider the positive direction in linear motion? From the direction of ACM. From the direction of ACM. So here you will consider the direction as according to the alpha. Okay, you can see that alpha here is in clockwise direction. So direction of alpha will be considered as positive. So alpha will be considered, clockwise will be considered as positive. Not take anyone as positive or negative. Okay, here it already has a alpha. Okay, if it already has a alpha, I have to consider that direction as positive. Okay, this is the rule. Okay, this is the rule which we used in linear also. That direction of acceleration is positive. So that is why here the alpha is also positive. If alpha is positive, the net torque can be written as C, F external into H minus Fs into R. Okay, F external into H is in clockwise direction, so positive. Fs into R is in the negative direction, that is in the anti-clockwise direction, so negative sign for this. Okay, this is equal to I alpha. I is moment of inertia. Moment of inertia in general can be replaced as mk square. Can be replaced as mk square. And we have already discussed radius of gyration. And alpha, how to replace alpha now? Just see. I told you that pure rolling, I can write VCM is equals to omega r. Okay. If VCM can be written as omega r, I can differentiate this relation. If I differentiate this relation, I can write ACM is equals to alpha r. Simple. Okay, dVCM by dt will become ACM and d omega by dt will become alpha. R is constant, so it will come out of differentiation. So ACM will become equal to alpha r. So from here, I can replace alpha as r. So ACM by r will be the value of alpha. Okay, this is I, this is alpha. Okay, so this becomes your second relation, second equation. Now see the variables which are there. The variables which are there are Fs and ACM. Fs and ACM.
Excuse me, sir.
Yes.
So could you please zoom out?
Okay, so there are two variables here. That is Fs and ACM. Okay, that is the frictional force and the acceleration of center of mass. External force, you are applying some external force. That means definitely you must be knowing how much force you are applying. Okay, so you will be given the value of external force in the question. No doubt in that. Okay, the mass of the object will be given. Okay, the height at which the force is being applied will be given. The radius of the object will be given. Everything will be given. Okay, only friction and ACM are the two quantities which are unknown to you. Okay, so you can solve it from here. Okay, so solving 1 and 2. Okay, if you solve 1 and 2, you will get the relation of acceleration of center of mass and frictional force. Okay, so I will directly write the result. Okay, in between there is mathematics. Okay, that is not at all important to us. Okay, nobody is going to ask us what is the derivation. Okay, the results is important. Okay, if you want the derivation, you can do it yourself. Just Fs can be written as MACM minus F external over here. Okay, use this result, replace it over here and solve. Okay, as you replace it in the second equation, you will have MACM. Okay, ACM will be calculated from that. So once you have ACM, you can replace ACM over here. You will have friction also. Okay, so I'm going to write the result directly. Okay, mathematics derivation is not important to you. So ACM. Okay, ACM comes out to be okay, this is the acceleration which you will get. Okay, of the center of mass. ACM will be this, and frictional force. The frictional force will be this will be the frictional force. Okay, so on solving 1 and 2, you will get this. Okay, it looks a very complicated kind of answer, but it is not. When you solve now, everything will set in its place. Okay, everything will be there as per the formula only. Okay, I have not done anything different other than basic mathematics. Okay, if you do the basic mathematics, this is the result you will be getting. Okay, I have just arranged it in such a manner that you will be able to remember the formula. Okay, you will be able to remember the result. Acha, now see here. One thing is important over here, that okay, if you are not able to remember the formula, doesn't matter, but the direction of friction force is important. Okay, and how can we calculate the direction of friction force? From the formula of friction. So what I can write here is, what I can see here is that if frictional force is having this formula. Now see, this is F external. Sorry, this is F external. And F external cannot be a deciding quantity. Okay, it cannot be positive or negative. It has to be positive only. We are using only the magnitude. Direction we have already considered. So only magnitude will be placed over here. So it is always positive. Okay, it is always positive. What about 1 plus k square by r square? Okay, if you see about 1 plus k square by r square, again it is always positive. Okay, 1 is positive, k square is positive, r square is positive. So it cannot be positive or negative. It will always be positive. But this term which is there, h by r minus k square by r square, h by r minus k square by r square, if it is there, okay, then your this friction direction will be changing. Okay, then your friction's direction will be changing. It can be positive, it can be negative, because there is a minus sign in between. You are subtracting two quantities. Okay, so let's see. There are three possibilities of friction. Static friction has three possibilities. Okay, what is that? Either it can be positive, static friction can be positive, either the static friction can be negative, or the static friction can be zero. Okay, what does positive, negative, and zero mean? Positive means the direction is same as F external. Okay, because see here, when I wrote the friction force, when I drew the friction force over here, I had assumed it in the same direction as F external. Okay, it is in the same direction as F external. If it is in the same direction as F external, then if the answer of static friction comes out to be positive, then the direction which I had assumed in the initial is correct. Okay, if answer is positive, it is correct, assumption is correct, so direction is same as F external. But if it is negative, it means that the direction is opposite to F external. Direction is opposite to F external. Okay, it is in the backward direction instead of being on the forward direction. And third case, static friction is 0. That means no friction, no requirement of friction. Okay, so if third case is possible, this means that you can do pure rolling. Okay, an object can show pure rolling even without the help of friction. So this becomes the important point. That friction is not a necessary requirement. For rolling motion, for pure rolling motion. Okay, just because of this single case, friction is not a requirement for pure rolling motion. Okay, so let's see the criteria. We will take a note in the last also. In the final, I will just make you write it as a note that friction is not a requirement. Okay. So first, let's see this. Let's see the criteria. Okay, static friction is positive. Okay, static friction is positive means what? That this term, this factor which is there, h by r minus k square by r square is greater than 0. It is greater than 0. Okay, so h by r minus k square by r square is greater than 0. Okay, so here you can write this, you can simplify this. H by r is greater than k square by r square. R will get cancelled. So this becomes h into r is greater than k square. Okay, h into r is greater than k square. Whenever such a thing is happening, that h into r is greater than k square, then your friction is in the positive direction. Okay, if it is negative, so let's see the criteria. Your h by r minus k square by r square should be less than 0. It is negative, so it should be less than 0. So h by r should be less than k square by r. R gets cancelled, so h into r should be less than k square. This is another criteria for negative friction. Take a friction in the opposite direction. And third is the last is the zero friction case. So in that case, h by r minus k square by r square should be equal to 0. If you solve this, you are getting an idea that hr should be to k square. Okay, so these are the three criteria which determine the direction of friction in pure rolling motion. These are the three criteria which determine the direction. Yes, just a minute. Okay, these are the three criteria which determine your pure rolling friction in pure rolling motion. I will give you questions also. Don't worry about that. We will see what kinds of questions can be asked. Yeah. Acha. So before that, just let's take a note. Okay, just let's write the note that what I was saying is that friction is friction is how it can be in the direction of F external. Acha, just try to understand what is friction. Okay, friction is a force which opposes relative motion. Okay, friction is a force which opposes relative motion or tendency of relative motion. Tendency of relative motion. Now just see. Okay, don't write all of this thing which I'm going to draw here now. Okay, just try to understand it. See here. I had an object like this which was rolling, Okay. Now when I ask the point at A, okay, when I ask the point at A, okay, that what is your tendency? Where do you want to go? Okay, with respect to the ground, है ना? If it says that I want to go in the forward direction, okay, suppose if the point is saying that I want to go in the forward direction. Why does it want to go in the forward direction? Because of the condition of rolling. Okay, its velocity VCM is greater than omega r. If VCM is greater than omega r, it has a tendency to go in the forward direction. Simple. Okay, we have seen that already. Velocity in case of velocity. Okay, so it has a tendency to go forward. But there is friction to stop this tendency. If it has a tendency to go forward, the friction will be applied in the backward direction. I guess no doubt in that. That is understandable. Okay, the tire, the point on the ground which is in contact with the ground wants to go forward, friction will be in the backward direction. But what if its tendency is to go in the backward direction? What if its tendency is there to go in the backward direction? Okay, so if the point A has a tendency to go in the backward direction, so what will the friction do? What will the friction do? It will stop this tendency. It will oppose this tendency. How it can oppose this tendency? By applying a frictional force in the forward direction. है ना? ठीक है. So in most of the cases, remember this, in most of the cases, in practical cases also, हाँ नहीं, I am just talking about the tendency. ठीक है, एक्चुअली में VCM is equal to omega r, no doubt in that. ठीक है, VCM is equal to omega r, no doubt in that. Just forget this. But I am talking about the tendency. Even in this situation, the point A has a it has necessity that it wants to go forward. Okay, if it wants to go forward, friction will pull it back. If it wants to go backward, it will pull it in the front. Okay, just try to imagine that your tire is rolling. Okay, tire is rolling. So in most of the practical situation, the friction is in forward direction. How? When your tire is rolling, okay, just imagine that this point comes here. This point comes here. So it has a tendency. It has a tendency to go in this direction. Okay, from a upper point, it rolls and comes to the point in contact. So obviously it will have a tendency to run in the backward direction. So if it has a tendency to run in the backward direction, the friction will do what? It will stop that tendency by applying a force in the forward direction. Is it understandable? And because it is not a physical class, so I cannot explain it to you in that manner which I can do there. But still, just try to see the situation over here. No. uh, how to explain this better? I cannot get any idea ठीक है, how to explain to you this online. ठीक है. So just for now, you can say that till now our physics was correct. ठीक है. Till now in physics everything was happening which was correct. ठीक है. So if here you are getting three relations, if you are getting three relation as per physics, ठीक है, physics is giving me this. So you can just for now assume that this is happening. This is true. ठीक है. When once your offline classes start na, ठीक है, then I will explain this to you physically. ठीक है, how this thing is happening. ठीक है, I cannot explain to you these things online. ठीक है, these are a few of the limitations of online classing. But ठीक है, everything else is done. ठीक है, you cannot go in depth in online classes, but ठीक है, I guess you can understand it just by seeing the physics. ठीक है, so just have patience. ठीक है, here I am also having some limitations, so I cannot explain it to you as good as I would have done it in offline. But still, just see that since physics is saying that there are three kinds of friction possible. Okay, since physics is saying that three kinds of friction is possible, one is positive, negative, and zero, and one is in the direction of external, one is in the opposite direction of external, and other is zero. Okay, so it can happen, it must happen, you can say, in fact. Okay. Or acha, you must be confusing. Okay, why you are unable to understand this is because you must be confusing it that, sir, if F external is there, then definitely the friction will be opposing that F external. That is wrong. Okay, it must be there in your mind, sir, ki hamesha F external is opposing. It is opposing force. But what it is opposing? It is opposing the velocity. It is opposing the tendency. It is not opposing the external force. It can be in the direction of F external. Or in fact, you can say it like this, that another let's just see. Suppose F external is acting like this. Okay, F external is acting like this. So what does this F external want? This F external wants to rotate the object in this direction. Okay, it wants to rotate the object in this direction. Okay, it is in the wrong one. Okay, F external is over here. F external is over here. So it wants to rotate. It wants to rotate the object in clockwise direction. Okay, but friction will do what? Friction will oppose this tendency to rotate in the clockwise direction. Okay, till whatever limit it can stop the tendency, it will try to stop it. Okay, it will stop, it won't stop, that is a matter of different thing. Okay, but it will try its full to stop the tendency. So what will the friction do? Friction will try to create an opposite rolling tendency. It will try to create a torque in the opposite direction. Why? So that it can stop the rolling motion. That is what friction is doing. It wants to stop the rolling motion. Okay, so it creates a force in the opposite direction. How it can create the force in opposite direction? By acting in the forward direction. Now in the second case, in the first case, you can say that if F external was like this, if F external was below the center of mass, now the center of the F external wants to create a rotational effect like this. But who will stop it? Friction will stop it. How can it stop it? By creating a rotational effect in opposite direction, by creating a torque in opposite direction. So if it wants to create a torque in this direction, the friction has to act in the backward direction. Okay, if it starts acting in the forward direction, it will supplement the rolling motion, and that is not the nature of friction. Okay, so it cannot be in the forward direction in this case. Now is it somewhat clear?
Yes, sir.
And I have just given a very rough idea. Okay, this is a very rough idea that when the object is below the center of mass, okay, friction is in the backward direction. When it is above the center of mass, it is in the forward direction. Actual में in reality it is not true. ठीक है, till some height h, ठीक है, you can see that till some height h is equals to, when h is equals to k square by r, when h is equals to k square by r, ठीक है, the friction becomes 0. So at some height h, that means friction is becoming 0. If the height is more than this, then the friction is in the forward direction. If the height is less than this, then the friction is in the backward direction. This is the situation that is actually happening. Okay, so I have given you a very rough idea for this. Very rough. It means it is nowhere in vicinity of your actual physics. Okay, actual physics says something else, that after some height, above some height, friction will be in the positive direction, and below some height, friction will be in the opposite direction. Okay, so that is why we have calculated these values. Okay, that is why we have calculated these values. If h is greater than this, friction is positive. Okay, friction is in the direction of external force. If it is below this, friction is in the opposite direction. Friction is in the opposite direction. Okay, so I am telling you, we will see questions. You will understand what does this relation, what does this result mean. Okay. Acha. So don't write these things, है ना? You have net issues. ठीक है, not much time is there. If you want, you can see the recording. ठीक है, if you have network issues. ठीक है, no problem. Not much time is there. Only 10 minutes is there. अच्छा, he's disconnected. ठीक है. अच्छा, so don't write all these things. ठीक है, these are कचरा. Extra only. ठीक है, no use. ठीक है. हाँ भाई, हाँ करता हूँ रिप्लाई. ठीक है. So what we were at note that friction is not a necessity. Necessary requirement. Necessary requirement for pure rolling. Okay, so this is a very important statement, that even without friction, you can create pure rolling motion. Okay, you can create pure rolling motion. This is the important result which we get from the three directions of friction. Okay, any doubts in this, anybody? Okay, so let's just take a quick look at a question. Okay, that suppose I have a disk over here. Okay, this is a disk on horizontal surface. Okay, mass is m, radius is r, and an external force is acting at point A. F is acting like this, and it is showing pure rolling. It is given in the question only. Okay, everything, whatever I am saying will be written in the statement. Okay, everything will be written there in the form of statements only. Okay, I am just to save time, I am drawing this. Okay, because almost it is done. So pure rolling is happening. Okay, you have a disk of mass m, radius r, and an external force is creating that pure rolling at point A. What is the question is that find the direction of friction. That's it, this much. Okay, this is the only question. Okay, what is the direction of friction necessary for this pure rolling condition? Okay, so just simple, it is simple. First of all, let's see here in this situation, your height is h. This is the height h, which is equal to r. You can see that h is equal to r. Okay, so LHS, if you see LHS, for the condition for finding the direction LHS, ठीक है, I had h into r. ठीक है, the LHS side was h into r. So what is h? It is r into r. It becomes r square. So LHS is becoming equal to r square. ठीक है, what about RHS? RHS was k square. RHS was, so for that you need the value of k for a disk. For a disk, first of all, write ICM if you want to find the value of k. For a disk, it is mr square by 2. ठीक है, then replace ICM by mk square. I told you equate mr square by 2 with mk square and solve this. So k square comes out to be r square by 2. K square for a disk comes out to be r square by 2. So if k square is equals to r square by 2, you can see that RHS is becoming r square by 2. Hence, I can say that LHS is greater than RHS. The left hand side is greater than RHS. That means HR is greater than k square. If you see the table, if you see this table, HR is greater than k square is true for the first case. Okay, it is the criteria for first case. Hence, without any doubt, I can say that the friction acting at the surface, at the contact surface, will be in the same direction as that of the external force that is on the right hand side, without any doubt. Okay, so in this manner, the questions are asked. Okay, about friction on horizontal surface. What is the direction of friction on the horizontal surface? ठीक है, any doubts anybody? है ना, so write it. ठीक है, your time is almost done. This chapter is over. ठीक है, your friction rolling is done. ठीक है, everything is done. है ना, so I guess you have exams on Sundays, so Saturday I guess physics exam है ना, something is there.
So
Friday
from
or
Saturday.
from Saturday है ना, I guess. So ठीक है, just revise these notes. ठीक है, do questions. I guess Thursday you have a holiday. ठीक है, so try to do as many questions on rotational as possible. ठीक है, because it is a big chapter. It is a big chapter. ठीक है, so it will take time. ठीक है, many questions are there. ठीक है, do as many questions as possible. And that's it for today then. Your chapter is over, है ना? Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. I guess everybody has written this.